Looks like in this practice problem, we've got a battery and a light bulb. So let me sketch that out actually. Battery and a light bulb, that'll just look like battery and a light bulb, which we can treat as a resistor. And what do we know about this? Same light bulb is connected to another battery and the current is twice as great. So in this one, we've got some voltage, some resistance, and let's say delta V is epsilon. So this battery has a delta voltage of epsilon. The light bulb has some resistance, and this causes some current to flow, presumably from the positive terminal of the battery around the circuit. So that's the current. And we are told that if we connect the same light bulb to a different battery with twice as much current, then the equation for power dissipated is quadrupled. So let's try writing these facts as equations, because it looks like this is listing out a whole bunch of facts and then trying to confuse you with how these facts relate to each other. So let's write each of those facts as an equation and see if we can make sense of it. Same light bulb is connected to another battery and the current is twice as great. With a different battery causing twice as much current, the equation for power dissipated by the light bulb is quadrupled because the power dissipated increases quadratically with the increase in current. So why is that? Which formula for power are we using here? If we're saying that twice as much current means 4 times as much power, what equation for power are we using there? Well, what are the available equations for, or the available formulas for power in a case like this? Yeah, I think I squared R will work well here, because we definitely know the light bulb has resistance and there's current flowing through it. So the power dissipated, that is the amount of heat and light leaving this bulb per second in joules per second or watts, should be equal to the current squared times the resistance. So this light bulb in this situation is emanating a certain amount of power. What this is saying is if you have a different battery that makes twice as much current, if you replace current with 2 times the original current, but then you square it, what happens to that times 2? Yeah, we get 4 times as big a result. Because if you multiply, whatever number current is, if you multiply it by 2, that times 2 gets squared, so the result gets multiplied by 4. So twice as much current, but the same resistance leads to 4 times as much power. So that seems to check out. We've got, if we use a different battery that provides twice as much current, then we also get 4 times as much power. Then it says, but the power supplied by the battery increases only linearly with the increase in current. And linearly basically just means directly proportional to each other. And why is that? What formula could we use for power supplied by a battery? Yeah, power is current times voltage, the epsilon, the electromotive force or voltage provided by the battery. So power dissipated by resistor versus power provided by battery. And if we have twice as much current here, and this is what it's getting at in the next part of the sentence, doubling the current only doubles the power supplied. And that seems to check out. If you have twice as much current, if you double current, you would double power because those are directly proportional. There's no squared involved. This would seem to contradict energy conservation because if we change to a different situation, we can't have the new battery provide twice as much power, but the resistor use 4 times as much power. Those should be increasing by the same amount. So energy conservation doesn't really seem to work in this case. We can't get twice as much power available, but then have 4 times as much power being used. Those should match. So what's the mistake here? What's wrong with this argument? Where is the trickery going on? Because this is absolutely a trick question. So where's the trick? Let's take a look at those equations one step at a time again. Power dissipated by a resistor is definitely I squared times R. We're getting twice as much current squared becomes 4 times as much power. And of course, it's the same resistance because it's the same light bulb. How are we getting twice as much current? What are we changing to make the current flow twice as fast? Yeah, we're changing the battery, right? So if we go to the power provided by the battery formula, twice as much current should suggest twice as much power. But specifically, what about the battery are we changing to get twice as much current? Yeah, we're changing epsilon. In order to get twice as much current, you need to change the voltage provided by the battery by what factor? If you want to double the current, what do you have to do to the voltage? Yeah, you also need to double it. And this goes back to Ohm's law. Or actually really the loop rule, I guess I would say. The loop rule here for this would say that the sum of all of the delta voltages in the loop adds up to 0. That's delta voltage for the battery and delta voltage for the resistor combined. What's delta voltage for any battery? Yeah, that's just the plus epsilon. And delta voltage for any resistor? Yeah, negative IR. If we solve that for I, what do you get? Right, epsilon over R. So if you want to get twice as much current by modifying the battery, you get twice as much current by using twice as strong a battery, twice as much epsilon. So according to the loop rule, the idea that the voltages have to add up to 0, and Ohm's law, the idea that the voltage on a resistor is negative IR, the only way you'd get twice as much current here is by having twice as much epsilon, twice as strong a battery. So it's not just twice as much power, you're doubling current and you're also doubling the voltage of the battery. If you double both of those, you get a ×2 and another ×2. So what is the multiplier actually? If you're doubling current and doubling the voltage of the battery, because that's the way you doubled current in the first place, yeah, ×2 ×2 combines to ×4. So it looks like these two approaches actually do agree. If you look at it in terms of power equals I squared R, you're doubling the current, so you get 2 squared, in other words, 4 times as much power. because the times 2 gets squared. Or if you look at it as current times voltage, you're doubling the current, but you're doing so by also doubling the voltage. So both of those get doubled, the times 2 and times 2 combined to get times 4. So either formula actually does lead to 4 times as much power if you double the current by doubling the strength of the battery. So I think this really is that's really the swindle behind this trick question, that if you just look at current, it looks like this formula leads to 4 times as much power and this formula leads to twice as much power. But you got to keep in mind that the only reason current is doubling in the first place is because the voltage is doubling also. So if those both double, then you're really multiplying the result by 2 twice, which means 4. Any other questions on that one? All right, then let's take a look at the hose one also. So I think the hose problem is basically getting into the idea of comparing a fluid flow system versus an electrical circuit system. We've got these hoses, and one end is connected to a high pressure water source, a faucet, and the other end is just open to the air. And we want to draw a schematic for an electrical circuit that is analogous to this fluid system. So in an electrical circuit, the hoses in the fluid circuit act like what in an electrical circuit? Like if you just got a hose or a pipe that fluid is flowing through, what does that act like in an electrical circuit? Yeah, the hoses act like wires. Although these are hoses that are presumably somewhat difficult to flow through. It's not infinitely easy for the fluid to flow through. So we shouldn't just call the hoses acting like wires. We should treat them as acting like what slightly more complicated situation? Like what property do these hoses have that makes it somewhat difficult for fluid to flow through? Why doesn't all the fluid just flow out immediately? What's holding it back? Yeah, these hoses have resistance. If they had no resistance, then the difference in pressure, I mean, if you go back to the Bernoulli equation, we've got delta pressure equals negative I times R. If you saw that for current, negative delta pressure over R, if you have no resistance, the current is going to be the difference in pressure divided by 0, and that's infinite. With no resistance, any difference in pressure would lead to infinite current, and that's impossible. Any hose, any pipe is going to have some resistance. If it's a very smooth, very wide, very short pipe, it might have very low resistance, but it's still not truly 0. So we should really treat these hoses as resistors, or at least wires with resistors in them. So to draw these out, we've got each of these sections of hose, the 10-foot section of hose and the 20-foot section of hose, we should treat as resistors. So we've got resistors, a resistor representing the 10-foot hose, another resistor representing the other section of 10-foot hose, and then we've got a resistor representing the 20-foot hose, and another resistor representing the other 20-foot hose. And it suggests that we call the resistance of the 10-foot hose R. And then this is another 10-foot hose, so that's also R. What would you expect to happen to the resistance if we just double the length of the hose, though? If you have a longer hose, would you expect that to be easier or more difficult for fluid to flow through? Yeah, more difficult. The longer the hose is, the more opportunities there are to lose energy by contact with the walls. And yeah, it should just be doubled to 2R. For fluid flow, and also technically for electrical flow as well, resistance of a pipe or resistance of a wire should be directly proportional to the length. And of course, for electrical resistors, usually we don't really care so much about the length. We just use slightly different materials or different thicknesses to modify the resistance in that way. So we've got two resistors, each of which has resistance R, and two more resistors, each of which has resistance 2R. And how are these connected to each other? We want to fill in all the equivalent connections, right? Like it looks like these 10-foot hoses are connected to each other on the left side. So we should have these connected on the left side. And they're also connected to each other on the right side. So we should have these connected on the right side. The 20-foot hoses are also connected to each other on the left side and connected to each other on the right side. So it looks like we should have connections like that, joining those together. And since these are joined together here, we should also have these joined together here. So we've got the 10-foot hoses, in other words, the resistors of resistance R, forming a loop, and the 20-foot hoses also forming a loop, and those loops are connected together here. Also, the left side of the 10-foot loop is connected to a faucet, and the right side of the 20-foot loop is connected to open air. And what's really the big difference between those? What's the biggest difference between the faucet and the open air? What's the difference between the faucet and the open air that we care about in the Bernoulli equation? Yeah, there's a difference in pressure. Presumably the faucet is high pressure. And the atmosphere is low pressure, specifically 1 atmosphere. So you create high pressure in the faucet to cause fluid to flow from the high pressure zone to the low pressure zone. Of course, for an electrical circuit, we're not talking about pressure directly. What's the electrical version of pressure? Yeah, voltage. So presumably, instead of having a high pressure zone and a low pressure zone, we've got a high voltage zone, relatively speaking, and a lower voltage zone. I guess I should say higher voltage and lower voltage, because we're not really making any statements about the exact values, just that one of them is higher than the other. And how do you cause that? What should we really be building into the circuit to make these voltages different? How do we force a voltage difference? How do we give a boost to voltage in a circuit? Yeah, we're going to need a battery. Also, for any current to flow, we really need a complete loop. So we should really be connecting these ends to each other. Connecting this to, and for the higher voltage zone, we want it connected to the positive terminal of the battery. So the positive terminal of the battery connects to the high voltage zone. The negative terminal of the battery connects to the low voltage zone. That forms a complete loop, including the battery. So that means current will actually flow. And the positive terminal creates a high voltage zone analogous to the high pressure zone from the faucet. The negative terminal of the battery creates a lower voltage zone analogous to the low pressure of the open air. So this electrical circuit is analogous to this fluid flow situation. In other words, it's going to act almost exactly the same, even though it's a different system. It's different stuff flowing. We've got charge flowing instead of fluid flowing. It's passing through wires instead of through hoses. The flow is caused by the push, the voltage from the battery, rather than being caused by the pressure difference from the faucet. But mathematically, it's going to lead to exactly the same sort of results. So this would be our electrical circuit. Any questions on that so far? Oh, and since we've got this battery, let's say that the battery just has voltage epsilon, where epsilon is some unknown value. And it looks like in the next section, we're going to need to figure out what happens if we make some changes there. If we step on one of the 10-foot hoses, in other words, if we block one of these resistors. So let's see what happens there. I think the idea here is we want to figure out how all this relates to the idea of current. Because presumably we're going to get current flowing, hits the junction, splits, joins back together, hits this junction, splits, and then joins back together. Any thoughts on how we would figure out how much current there is? Like if you just wanted to find the current in this situation. We could use the loop rule, yeah. The problem is the loop is going to be kind of complicated. We're going to have the option of splitting this way or splitting this way. We could go the upper path or the lower path, and then they join back together. And then we could also go on the upper path here or the lower path here. Yeah, I think finding our total is probably going to be easier in this case. If we can figure out the total resistance, then we can just use the simpler loop rule by treating it as just one battery and one big combined resistor. So let's see if we can find the total resistance of all this. And that'll give us information about the current through the battery. So how would you combine these resistors? What resistors? Yeah, we can combine resistors in parallel. For instance, these two resistors R and R are definitely in parallel with each other. So we can combine those. We can say these resistors together just act like one big resistor. And how would you calculate what that total resistance is? Yeah, they're in parallel, so we add 1 over R plus 1 over R. If they're in series, we just add R plus R. But since they're in parallel, we're going to have to add their reciprocals. We would say 1 over R equivalent equals 1 over R1, which is just R, plus 1 over R2, which is also R. In this case, we don't even need to find a common denominator because they're already both over the same R. So we can just combine those. 1 over R plus 1 over R is 2 over R. And then how would you find R equivalent? Yeah, we flip the fractions, we invert both sides. Formally, if you need to justify this mathematically, you could say you're raising both sides to the -1 power. Because a fraction to the -1 is its reciprocal. So R equivalent over 1 is R over 2. So that means these two resistors together act like just one resistor whose resistance is R over 2. And note that that's lower than either of these resistors individually. If you combine several resistors in parallel, the resulting equivalent resistance is going to be weaker than any of the resistors individually, because the more different paths you have, the easier it is for fluid or for charge to flow. So more resistors in parallel, adding more paths always makes it easier for current to flow. And then if we take a look at the other one, we've got these two resistors also in parallel. So these two resistors together, what are those going to act like? We'd set it up the same, but notice that these resistors are 2R and 2R instead of 1R and 1R. So what would the result be there? Yeah, just R. And you could work out the numbers again. You could say 1 over R equivalent equals 1 over 2R plus 1 over 2R. That combines to 2 over 2R, and the 2's cancel out, so we just get R. You could also look at this as this is exactly the same setup. We're just doubling all the resistances, so that also doubles the equivalent resistance. So it looks like our total resistance, we've got this acts like a single R over 2 resistor and a single R resistor. And how would you say those two big resistors are combined? If we just have this strangely shaped big green resistor, yeah, and this strangely shaped big pink resistor, those are now in series, right? Because current flowing through the green blob has to flow through the pink blob as well. So now the combined resistors are in series with each other, so we can just add them together. R over 2 plus R is 3R over 2. So the whole thing acts like just a single resistor with resistance 3R over 2. Let's say R total is 3R over 2. So that's the total resistance of the whole thing. And the current, if you know the total resistance, we can just use the loop rule, the simplified loop rule. Again, delta V for the battery plus delta V for the one big resistor is 0. So that's our usual epsilon plus negative IR equals 0. And then we solve for I, and specifically this is going to be current through the battery because it splits when it hits the junctions. But the current through the battery is going to be epsilon over R. And that's R total, which we now know is 3R over 2. So we can even fill that in. Epsilon dividing by 3R over 2 is the same as multiplying by its reciprocal, 2 over 3R. So the current through the battery is going to be 2/3 times epsilon over R. So that's the current with the circuit exactly as shown. And of course, the current is going to split when it hits the junction. Would you expect it to split evenly or for more current to go through one branch or the other? What happens when the current hits this junction? Yeah, it's going to split evenly. And how do we know that? Why wouldn't we get more current to one branch or the other? Yeah, these two paths have the exact same resistance, so there's no reason to expect one of them to get more or less current than the other. The current splits evenly into exact halves, so 1/3 epsilon over R and 1/3 epsilon over R. And then they join back together into 2/3 epsilon over R. Then here it also splits evenly exactly into two equal halves because there's no difference between these two paths. And then joins back together to get the full circuit, full current again. Any questions on that so far? But then in part B, we change the circuit. We step on one of the 10-foot hoses. So we are blocking one of these resistors. By the way, if we're just blocking one of these resistors so no current can flow through it, would you say that acts more like a short circuit or more like a burnout? Yeah, that's going to act more like a burnout. It just blocks current from flowing entirely through one resistor. Whereas a short circuit provides an alternate path, making it easier for charge to flow. In this case, though, we're changing the circuit. We are effectively blocking off one of these resistors. So I'm just going to delete that resistor from the system, which means we're going to have to rethink the total current or total resistance because we've cut off one of the paths. Before we even run any numbers on this, conceptually, if we block one of the paths, would you expect that to increase or decrease the total resistance? And why is that? Have we made it easier or more difficult for fluid to flow or for current to flow? What happens to the total resistance if you add more and more paths? Like if I were to add an extra path here, an extra path here, extra path here, it might help to think of this in terms of traffic flow on roads. If you've got one road linking two cities together, you're probably going to have a lot of traffic. If you add another road, a side route, is that going to make it easier or more difficult for traffic to flow? Yeah, more paths makes it easier to flow because there are more options. You get, I guess you might say, less congestion because there are other paths for charge to take. And yeah, we could also look at this in terms of the equation. We previously had the cluster of two resistors was R over 2 in total. By removing a path, we've increased the resistance to R. Adding extra paths in parallel always makes it easier for current to flow. So removing paths, cutting off options, makes it more difficult. So every time you remove a path, you're increasing the total resistance. Now, if they were in series, chaining more resistors together in series increases the resistance. But putting more resistors together in parallel means you're adding extra paths, extra options. And that always makes it easier for current to flow. So with that, with one of the paths cut off, we now have higher resistance, and that should suggest we're going to get less current or slower current. In fact, now what is the new total resistance? I should probably say the old total resistance and the old current. Yeah, if we now add these together, we've got R and then another effectively R in series with each other. So we can say that the new total resistance is 2R. Higher total resistance, so we should expect less current. We can still use the same current equals epsilon over R total. In this case, that'll be epsilon over 2R. Or in other words, the new current is going to be 1/2 times epsilon over R. So those are the currents we want to compare. The old current was 2/3 epsilon over R. The new current is 1/2 epsilon over R. Oh, and we also are saying that the original current, if we go back to the idea of fluid flow, the original current, the old current, was 8 gallons per minute. So we can say this is equivalent to 8 gallons per minute. Now we want to know what's the new current in terms of gallons per minute. So how can we compare those? If we're saying that 2/3 epsilon over R is equivalent to 8 gallons per minute, how can we figure out, yeah, we can isolate epsilon over R, right? We can say epsilon over R, if you just treat epsilon over R as your unknown variable, how would you isolate epsilon over R here? How would you get rid of that 2/3? Yeah, multiply by 3 over 2. So we get 3 over 2 times 8 gallons per minute, which is 12 gallons per minute. So the value epsilon over R, even though epsilon over R is talking about electrical current, it's equivalent to the 12 gallons per minute from the fluid circuit that we were looking at earlier. So we can plug that in over here and take 1/2 times epsilon over R. One half times, we know epsilon over R is equivalent to 12 gallons per minute. So we take half of that, we get 6 gallons per minute. So we should expect that with one of the hoses blocked, instead of getting 8 gallons per minute, it's reduced to only 6 gallons per minute. Because we've increased the total resistance by cutting off a path. So that decreases the current flowing through the hoses. Any questions on that? Or any other questions on electrical circuits in general? Then let's take a brief look at the idea of capacitors while we're here. Can you see the blank screen all right? Does this show up? Okay, cool. Just wanted to make sure this is visible. So capacitors. What do you know about capacitors so far? Like, what is a capacitor? The basic idea, if you wanted to build, it's essentially a device for storing charge, and specifically storing charge in a way that creates a voltage of its own. The basic idea of a capacitor is just a pair of metal plates with a layer of insulator in between. So let's say you have this metal plate. Let me make this a different color. Let's say, no, this will work. Let's say this is a metal plate. I'm trying to draw this in 3D here. So this is like a square flat on the ground. And then you have a layer of some sort of insulating material, insulating in the sense of material that does not conduct electricity. You know, I think the hollow one is not going to work. Let me put it this way. So you've got a square of metal, and then on top of that, we're going to stack a square of some sort of plastic. So maybe plastic, maybe glass, maybe even just a layer of air. And then on top of that, another layer of metal. So metal, plastic metal, or metal, glass metal, or even just metal, empty space metal. The important thing is metal can have charge on it. The definition of a metal, a conductor electrically, is that it's a material that charge can flow in easily, that charge can just move around freely within the metal, within the conductor. So we can have all sorts of charges just moving around on the metal plates, but the charge cannot move through the insulating layer. Which means if we have some wires connecting here, let's say we have some wires that connect from this plate, and let's say to a resistor, and then to a battery, and then to this plate. Does that form a complete loop? Technically, no, right? Because there's this gap here. There's this layer of insulator. And the definition of an insulator is that charge cannot cross that material. We have this gap that charge cannot jump across. So technically, this is not a loop. But the reason why this is different from just, like, if we just had, like, if we just had a battery and a resistor and then a gap, In this case, with just a gap, definitely you have no current flowing. There's nowhere for the charge to go. But in this case, the fact that these metal plates are large means that they can store a lot of extra charge. So if you have, let's say you imagine charges moving around on this circuit. If you have, let's say, a bit of well, positive charge isn't really moving. Let's say you have a bit of negative charge. If you have, let's say, an electron, a little blob of negative charge, what is the negative terminal of the battery going to do to this negative charge? Yeah, the negative terminal of the battery it repels the negative charge. Now, if we were talking about this situation, that charge won't actually move because there's nowhere for it to go. This gap means it can't actually go anywhere. Because it's not just that one charge, of course. There's electrons all along this wire already. The battery isn't producing electrons. The battery is just pushing on the electrons that are already in the wire. But this chain of electrons has nowhere to go because there's this gap. But if we have this big metal plate, there's actually somewhere for the electrons to go. If you take a look at these individual electrons, then the battery provides a push and the electrons actually have somewhere to go because there's plenty of extra space in the conducting plate for the electrons to move into. And of course, you never really run out of electrons. There's always more electrons available, especially because electrons are also in the other wire, the other section of wire. What's happening to these electrons compared to the positive terminal of the battery? What would a positive terminal do to negatively charged electrons? Yeah, positive and negative are going to attract. So the negative terminal is pushing electrons away. The positive terminal is pulling electrons in and through. And again, in the situation where there's just a gap in the wire, it can't do that because the electrons can't be pulled away from that empty space. But in this case, the thing is the conductor already has lots of electrons. It's not just empty. The conductor is made of atoms, which consist of electrons and protons in equal balance. But because the conductor is large, the battery is actually able to pull charges through. Pull the electrons through and pull electrons out of the conductor. So this plate, the back plate here, gets electrons pulled out of it. And if electrons are pulled out, what's left behind? What's still there? What do we now have extras of if we've removed some electrons? Yeah, the protons are still there. The protons don't move at all. So we essentially leave gaps in this conductor where there were electrons, but now there aren't. And those gaps act like positive charge. By pushing extra electrons into one conductor, we've made that conductor have too many electrons, so it is now negatively charged. But the other conductor, we are pulling electrons out of it, but leaving the protons where they are. By removing electrons, that conductor becomes positively charged. And of course, there's no current crossing over the gap. The insulator prevents any current from jumping from one plate to the other. But overall, if you take a look at where charges are going, we've got electrons moving overall in this direction. So even though there's no charge crossing this gap, overall we still have charge flowing. And it can't last forever because as charge builds up on the plates, let's say you get more and more negative charge, more and more electrons building up on this negatively charged plate. What do the electrons that are already there do to the new electrons that are trying to come in? Yeah, they're going to repel, which means that the more negative charge accumulates on this plate, the more difficult it is for new negative charge to flow in. And likewise, as the other conductor becomes more positively charged, it's going to try attracting the electrons that are attempting to leave. So that means it becomes more and more difficult for electrons to leave this plate and more difficult for electrons to enter this plate. So what would you expect to happen to the flow over time? Yeah, it's going to get slower and slower. If the plates start off neutral, no extra charge on either one, then you get fast current flow because of the battery's push. But as the plates start to accumulate more and more opposite charge, the battery is still pushing with the same strength, but the conductor is pushing back in the other direction, or the capacitor, this sandwich of plates. The charge on the capacitor is pushing back with growing greater and greater strength. And so that means the current starts to slow down. And this ends up leading to exponential decay. You get very fast current at first because there's no pushback from the plates. And then as it fills up, you get more and more pushback, meaning the current gets slower, meaning the plates fill up more slowly. And so you get this feedback loop of slower current means the plates fill up more slowly, but they're still filling up. So that means more pushback, which means the current gets even slower and slower and slower. And it ends up forming exponential decay patterns in both the charge versus time graph and the current versus time graph. Although we're gaining charge, so it's actually going to be exponential decay upwards towards a non-zero asymptote. But capacitors, this idea of these sandwiches of parallel plates tend to lead to exponential decay patterns for that reason. Any questions on that so far? Oh, and one other thing on capacitors, I've been talking about the pushback from the capacitor, but what is the electrical term for a push? When we say an electrical push, what do we really mean? What's the formal term for that? Well, what do we call it's not quite power. Power is more about how quickly energy is being produced or used up. But what do we call, for instance, the push that the battery causes? The battery provides a boost in what? How is a battery typically labeled? Like a battery would say like 9 watt or 1.5 watt volts. Exactly. The electrical push, the electrical equivalent of pressure is voltage. When we say that something is pushing on the charge, we're really talking about the voltage it has. So the battery is providing a constant voltage, a constant push. The capacitor is pushing back with a voltage of its own. And the capacitor's voltage, delta V capacitor, ends up being proportional to the amount of charge on it. If there's no charge on the capacitor, there's no voltage. But the more charge accumulates, the more voltage pushback you get. So the delta voltage of capacitor is proportional to charge Q that's stored on it. And also a constant proportionality we call C, the capacitance. So the delta V for the capacitor is Q over C, where Q is the charge that's stored on it so far. C is a constant called the capacitance that's basically a measure of how efficient the capacitor is at storing charge. And also typically there's a negative sign because it's a pushback against the direction of the push, or against the direction of the battery in this case. So that's the usual formula for the delta voltage of a capacitor. And you can use that in the loop rule equations, just like voltage for a battery or a resistor. Any questions on the capacitor so far? All right, then we'll look into more about capacitors next time and how they lead to exponential decay and maybe some examples of that. In the meanwhile, let me know if you have any questions for next time or other examples you'd like to try out, and I will see you then.